We have finished a basic introduction to electrostatics, and now it's time to press onward and look at, you could say, electrodynamics, but I'm calling this unit direct current circuits, and there are some basic introductory ideas I would like to convey. So what we've been doing with electrostatics is considering charges that are stationary. They're not moving. So electric current, as you can surmise, are charges that are moving. There's a pretty big difference. Now for charges to keep moving, they have to move through something. They can't just move through the air very easily. What we're really talking about is a complete circuit, a complete path for charges to flow. And in other words, it's a loop, a conductive loop of some sort. Now, as the charges flow, as they move, they lose energy because it takes some energy to get them to move. So that makes sense. During their motion in a circuit, they require some way of continuing to move. In other words, if you just say take a ball and throw it, it's going to lose energy as it drops toward the ground. Certainly as it hits the ground, some of that energy is converted to heat because it's not a perfectly mechanical system. So there's got to be a means to boost the energy of the ball, or in this case the charges, as they go around the circuit. And the object or device that does that boosting has several names. I'll start by calling it a charge pump, basically pumping up the energy of the charges. More commonly, it's called a power supply. Another synonymous term, current source or a voltage source. Those are all synonyms. And you need one or more circuit elements to make a complete circuit. So I'll show you one here. There it is. This is about as simple of a circuit as you can possibly imagine. Okay, there's a lot of whining of dogs down there in the downstairs, and it's probably coming through on the recording. So let me shut this door. Poor dogs want to have their total freedom, but they get into a certain amount of trouble when you give them too much freedom. So a little bit of confinement in their cages every now and then. No, we're not abusing our animals. All right, so now the charge pump. Well, here, so I was showing you this circuit. Basically a source. This is the charge pump or power supply, and it's going to send charge through this element. This could be a light bulb. This is basically here a flashlight. If you put a switch in here, you close the switch. If this is a light bulb, the light bulb lights up. Simple as that. Connected with wires to make a complete loop. In fact, the charge pump is typically a battery. In terms of what most people are used to, with most of the devices that you operate day to day, there's so much portability now. So your smartphone has got a battery, and that is the charge pump to run the thing. Magnetic charge pump is called a generator, and that's very common as well. Your automobile has that, a spinning generator that produces electrical current to keep the battery charged. That's in there, and also run the electrical devices. We're going to spend a little time on circuit symbols, just a few of them, but I want you to know how to construct the symbol for a battery. So it's basically just a longer plate and a shorter plate symbol here with plus and minus, and V for voltage source. The plus side is the long side. The short side is by definition the negative side of the battery. Positive and negative, opposite charges, right? And then a generator. Typically generators are alternators, namely the electricity is produced in one direction and then the other. So here's a basic symbol for that. This isn't something you have to draw very much, but we're starting here in our discussion with basically the power supply, and considering that a circuit, in brief, is a complete path with the power supply, the circuit element, and a loop. And we're going to progress on toward the circuit elements and to study them a little more. So just a brief and quick rundown of some of the common circuit elements, or items, components, different names, that are in a circuit that have function, typically, in various ways. We have resistors, very common, capacitors, switches. Everybody knows what a switch is, probably. Capacitors, perhaps not. Fuses, lamps, coils. Big one is semiconductors. Certainly really huge in almost anything that we have nowadays, like your smartphone and computers are loaded with semiconductors. And they're all connected with wire to a power source, forming a complete loop. So here's some of the symbols. A resistor is just basically a squiggly line here. And that's standard schematic symbol. Switch looks like a switch. Lamp might look something like this on a schematic diagram, or really a lamp traditionally. It's not an LED lamp now they're becoming more common. It was just a resistor, basically a piece of nichrome wire, which is just a resistive wire. Then a capacitor, symbolized by two parallel plates next to each other that stores charge. Fuse, basically a squiggly line that will open if too much current flows to protect the circuit and maybe protect the individual. Coil tends to look like a coil. Wire crossing. So you got wires going all over the place. We want to cross a wire with another one. How can you tell which one is which? Well, something like this gives you a good idea. There's a start. And now let's just kind of get into the electrical quantities. To start with, we have current. The symbol is I. And what is current? Current is probably the most fundamental idea. Without current, you don't have anything happening. Basically, current is the rate at which the charge is flowing. So the rate of charge flow, and that's with respect to time. So in other words, it's charge over time, Q over T. Now Q over T is coulombs over seconds, standard units. That has another expression, another definition. It's called an ampere. Now amperes would then be the fundamental unit for current, often referred to as just amps for short, and the symbol is just capital A. So that is the definition of current in any circuit. Before going any further, let's go ahead and look at an example circuit. And a lot of what I want to discuss here is just pretty much common sense. It's a little more probably easy to understand by demonstrating it, which if you're taking my class, you'll have seen it, or you will see it in action. But here's the circuit, and we have a power supply, basically a battery, a switch, a resistor, which in this case is a lamp, is a loop. Then there's another loop that has a capacitor and another lamp in that loop. So that's the basic circuit. Now I'm going to close the switch. Now what happens? Well, now we have a complete loop from the source where current can flow. Current can flow around here, which is pretty reasonable. And the current, the charge per time that we just defined, is I for current. Now when it gets to this point, it doesn't have to split evenly, but I hope you can see that it has the opportunity to split. Some can go down here, and some can go this way. And in fact, that's what happens. So I'm going to call this current I1. And then on the other branch, I'm going to call that I2. Now a capacitor is an electrical component that is designed for charge to build up on one plate. So we'll have positive charges building up on this plate. Since likes repel, they push off the positive on this plate, shoves it off, and the current continues to flow. And it's the same current. The same current I2 in here is the current I2 flowing out. So you would expect both lamps to light up. And in fact, they will. However, as this capacitor builds up charge, it pushes back on the source that's trying to put the charge there in the first place, which is the power supply. And so by pushing back, it pushes back harder as more charge builds up on here. pushing off charge here and continuing the current. So when that's built up enough, it pushes back so hard against this that it stops the flow. So I just kind of gave you all the answers there. Except, well, this is another idea here, namely that the current that flows around here and here recombines after this junction. So the current coming out of the battery, that's split here and here, is reunited here and here to I1 plus I2. The other thing that I just want to mention real briefly is that even though I talk about charges, we think about them marching along here and seeing the resistor and then making its way through the resistor. Really, it's a domino effect, like water in a tube, where you put water in and water flows out the other side of the tube almost instantaneously. Basically, the water in the hose all moves at the same time. Likewise, the charges in the loop are all moving at the same time. So as soon as charge starts moving out of here, it's moving everywhere in this circuit, in this branch and in this branch. But to get an initial functional understanding, it sometimes is helpful to think of the charges moving along and encountering these components. The problem is, you might think over here, I got to decide what to do at the capacitor, and once I'm done with that, I'll decide what to do here. Well, no. Any charge going this way is then also moving everywhere else in this loop. So just keep that in mind. Now, a description of what's going on. So we close the switch. The voltage source sends positive charges. That's the definition of electrical current, is the flow of positive charge, which is just really the opposite direction of the flow of electrons. So electrons move in one way, or negative charge is how I'd like you to think about it, is like positive charge flowing the opposite way. And that's the standard definition for electrical circuits, is the direction that positive charges move. And it goes through R1 back to the negative side of the battery. That's just expressing what's going on here. The lamp lights up. The battery pumps up the energy of the charges, and so they're ready to continue doing their deeds, which is to continue to flow. Because otherwise, it's like water flowing down a hill. It loses energy, and unless it's pumped back up, whoop, it doesn't flow anymore. Now the resistor is a restriction to the flow of charge, and what it effectively does is reduces the energy of the charges. It takes away some of their energy, and that energy is given off as light and heat in a typical lamp. So that's lost energy. But that's what you're trying to do, is light the lamp so you can see. Don't necessarily want to waste the heat. The light is what we want. And as I mentioned a little bit ago, I think LED lights are really efficient at producing light rather than heat, which is usually wasted. Unless it's really cold outside or inside, and you're kind of happy for that lamp that's also acting as a heater. Well, now, at the same time, charge flows on one plate of the capacitor, and then off the other plate and through R2. Back to the source, and it gets pumped up as well. So those charges come around here and get pumped up, and this process continues. So after a long time, as the charge builds up on this plate, I already mentioned how it's pushing back, it reduces the current that's traveling along here. It doesn't reduce this path. There's no restriction, well, other than the resistor. So that stays constant. But the current here is reduced because of the buildup until this lamp, the current going through the lamp, goes dimmer and dimmer as the capacitor gets fully charged, and then the lamp goes out. So that's what happens if you see the demonstration of this. And then we're going to take the switch and go whoop and open it up. Now what happens? Well, if we open the switch, it removes the battery from the circuit. The battery is no longer trying to push charge onto this capacitor. You open this up, it's like taking this whole left half of the circuit and throwing it away. And now this positive charge here says, aha, I can't go back against the, just before it was fighting the power supply. But now that's disconnected, so it can now push off and go down through the resistor like this. and around like this through this resistor, which is, notice, the opposite way that I2 was flowing originally. But in this case, the capacitor is acting like a battery, and it pushes this charge to R1 and R2. So it's kind of like before, the battery just had to go through this one resistor back to the source, and another path around here, a separate path. The capacitor has to push charge through both of these as one path. So it has a harder time doing that. So these lamps will immediately, when we open the switch, relight up, but dimmer, and then both of them will just go out completely as the capacitor discharges itself. So that's a briefer on this particular example circuit. Hopefully some of that made sense. It will all become clear as you work with this hands-on in labs and process it more with other situations.